Okay. So, we talked so far about going from parametric and back to rectangular, which has been super awesome. We talked about isolating the t and substituting into the other equation, okay? So just real quick, we do a couple examples where we take something that's already in rectangular format, like function mode, and put it into parametric. It's super duper sweet and easy. Ready? If you have it in standard form, not really standard form math-wise, but we always like f of x equals something with x's in it. The easiest, most simple way to turn this into a parametric equation is to just let x of t be t. Because if x of t is just t, then all y of t has to be is exactly what it was, but x is now t. So we can do it like that. Simple enough. Now that's parametric. I know, right? Yeah. So look, there isn't just one answer to this. Remember we talked about how you can graph like the same exact graph, the same picture, multiple ways. You can graph it backwards, you can graph it faster, slower. There's many ways to parametricize, to turn an equation into parametric equations, okay? Yeah, good. Okay, so for instance, instead of calling this t, and there's really no benefit to doing this, I'm just going to show you how this like affects the graph and everything, okay? I could have said, hey, let's let this be 4t. You with me on this? But whatever I let x be, now y is just going to be the same thing, but wherever I see x, I'm going to put 4t.
So wouldn't it just be 8t squared?
It'll actually be 32t squared, because you got to square the 4 as well. Okay? But I'm just going to plug it in like this for right now. Can we handle that?
Yeah.
What will the difference be between just calling x t and calling x 4t if we graph them? They're going to look the same. When it's done, all said and done. What's up? It isn't going to be stretched. It's going to look exactly the same. It's not going to change the graph. What? We could change the direction it travels in, but this is not going to do that. These are all excellent guesses. The coordinates are all the same, though. X is going to grow faster because it's 4t now. Does that make sense? So all it's going to do is graph the parabola faster. That's it. Does that make sense? Now every time t goes up 1, x goes up by 4. If I wanted to graph it backwards for whatever reason, normally we graph x goes from left to right. Right? Well, your left to your right. Cool. That means as x gets bigger, the y just moves from left to right. Well, if x just equals a t, or positive t, that's going to happen the same way. It's still going to graph in the same direction. But if I made x equal negative 4t, now it's going to graph it backwards, because as t gets bigger, x gets smaller.
So it graphs slower?
It's the absolute value that dictates whether or not it's going to go faster or slower. To make it graph slower, what kind of number would I have to put in front of t? Like a half or something. Yeah, that would make it graph slower. And just so we can see this in incredible action, let's just go ahead and graph the two things, and you'll see them both pop up. It's going to be awesome. I'm overselling this. Okay, so we'll have t, and then we'll have, so this is going to be the first one. No. 2t squared. Hello, Alex.
Hello.
Plus 3t. That's going to be the first curve. And then I'm also going to graph 4t and 2 times 4t squared plus 12t, right? You okay with this? Good, me too. Excellent. Resounding yes. I'm going to change this so you can see the circle, so you can watch them graph. Because if I didn't put the circle thing happening on there, then you would just see one get graphed, and then it would look the same the whole time. But check out this craziness. Let's change our window, I guess, to go from like -10 to 10. Come on, calculator, work with me here. All right, you ready? So, there goes 1. It's so incredible. Look at it go. This is just amazing. That was so exhilarating. Maybe I lied. Where's the other one? Hey, there it comes. There it goes. See how it took it forever to get there? It's like your little baby brother is tagging along behind you super duper slow. Okay? Anyway, that's it. Look, they look exactly the same. They both follow the same exact curve, just one moves faster than the other because one is growing 4 times the speed as the other one, okay? Easy enough? But it doesn't change the shape of the graph, which is weird. Because I know, like you guys are saying, if you put a 4 in front of it, it should stretch it or something. That's not going to happen in this case because I changed the y equation as well. Simple enough? Okay. My pen died? My pen died. So if for some reason we have x equals a y squared, then it doesn't make sense to let x equal t in this case, because then we got to deal with the whole y thing going on. So if y is built into your equation, just let y equal t. Anybody know what this graph's going to look like? No takers? Michelle, no? You're like, yeah, whatever, it's a graph. Just let it do its thing. It is a parabola, but which way is it opening? Nah, to the right, because it's y squared. Okay? If x equals y squared, it's a sideways parabola opening to the right.
Wait.
Yeah?
Why does it make that one, like, one was going up, so why does this one go to the right? If they're both in
Because the first one, and we're going to do a unit on these kinds of weird graphs, but the first one had x squared in it. Y was an x squared. Okay? This one is x equals a y squared. So we're basically kind of like inversing it a little bit. But anyway, I would just let y equal t in this case, and then x would just be t squared minus 8t plus 12. Nothing crazy. Easy enough? There's not a ton of point to this unless you have like an idea of how you want it to be graphed, like how fast you want it to go, where you want it to be.
Why does it matter if it's moving faster?
So again, the point of these isn't just to get the same graph, it's to talk about motion. Okay, so like you want to match the motion that you're trying to map, which, and like just doing this is almost kind of pointless just to get it. Like there's no reason to turn this into parametric. I'm just showing you how to do it in case it ever pops up somewhere. Okay, but really we want to talk about motion, I guess.
Wait, like for our test, how are you doing?
It'll look just like this. Okay. Here, let's pause this. Hold on. All right, let's discuss. Good plan. Okay. Yo, guys, to find the equation of a line, we're going to do, I'm going to show you two different ways to do this, okay? The first is you can just find the equation of a line like normal, like y equals mx plus b if you want, or you can use point slope form, okay? And then just convert to parametric the way that we just did. All right, what's wrong? Oh, you guys are good, okay. So, the slope of this line is, hopefully everyone can do this, it goes up 5, it goes from 5 to 10, the y value, so it goes up 5, and x goes from 2 to 6, so that's over 4. So the slope is 5/4. Easy enough?
Yeah.
Now, I know a lot of y'all love to use slope-intercept form. Okay, I'm going to skip over that for a second and just say that you should use point-slope form. Okay, because it requires less work and I think it's a little bit easier. Okay, and all point-slope form is this. You ready for this? It's y minus, you just need one point that's on the line. We have 2 points. It doesn't matter which one you pick. They'll both give you the same answer in the end. Okay, I'm going to pick the first one just because it's first. So y minus the y value equals the slope of x minus the x value of the point I chose. Okay with that? Now, I know we're used to looking at this in just y equals form, so we can solve this for y equals. Check this out. You get y equals 5/4 x minus 5/2 plus 5 with a little bit of algebra. Are there any questions on that? I distributed the 5/4 and I added 5. And then we can add fractions up. Yeah, so minus 5/2 plus 5. Keep in mind, 5 is really 10/2. So negative 5/2 plus 10/2 is 5/2. So that's slope-intercept form. If you got that, excellent work. Yeah. And solve for B, yes. So, another way you could do this. What's wrong? Okay, another way you could do this is once you find the slope, you can go this route. Y equals 5/4 x plus b, and then plug in one of the points and solve for b. Okay, which I imagine is how you probably did it mostly in Algebra 1. Okay, that's fine. That'll work too. I like point slope form though because it doesn't require any algebra. You just got to simplify a little bit. But anyway, the answer is 5/4 x plus 5/2, but that's not really the answer we're looking for. I want that to be in parametric equations. So once I get that, I'm just going to say, great, let's let x equal t, and then y should just equal I think it's actually French. No, I think that's a German accent.
It is not German accent.
Korean?
Smart.
No?
Rob.
All right. Yo, are there any questions on this? Everybody feel like they can do this? All we did was find the equation of a line and put a t in it instead of an x. Okay.
X equals that equation, we have to put y is c.
Huh?
If it was x is 5 for t and stuff, y should be that t, right?
Yeah. Okay.
Are we learning anything?
Yeah, we're going to keep going through these notes here. Come on. Why is there so much talking happening right now? If you got to pass, go ahead. What are you doing, Mun? Michelle Munn. What are you coming over here for? What do you want? Michelle, I can't believe you would do that. Now it's on YouTube, see? It's so funny. You guys are duds.
Oh, this is on YouTube?
Our jokes are funny. All right.
Mama, I'm famous.
Here's another way you could do it. Yo, question 4, same exact thing. Same exact thing, but I'm going to show you how to do it with some vectors, okay? You're going to love this. Well, we are missing 4 kids. Maybe we shouldn't go any further. Look, another way to do this is to take, not a 5, is to take the first point you're given and write it like a vector. That just means put those little brackets on it. That's not any huge thing. Okay? And all we're going to do is take that point and add the vector we need. It's going to seem weird to get to the next point that I want. So to go from here to here, how much does y have to change?
5.
It has to change by, well, x has to change by 5. That's fine. Y has to change by 3. So I want to add in that vector. Does that make sense? Now, let's think about this. That vector actually has a direction, right? And that's the direction of the line. So if I add any multiple of that vector, I won't land on that same point, but I'll still be on the same line, if that makes sense. Okay? Because I'm adding the same direction over and over again. So one way you could think about doing this is you're really adding some multiple of that 5, 3 vector, because that's going to get you in that same direction. And from here, we can get to parametric equations just like this. Check this out. What's my x component going to be if I add these vectors together? Well, if I add in the 5 and negative 3, it is going to be 2. But I'm adding in 5 times t. So it's actually going to be, 5t minus 3. The 3 doesn't have a t on it. It's really negative 3 plus 5t. That's what I want x to do. I want to grow by 5. Is that okay? And then y of t would be negative 2 plus 3t, which is just this. You could have done the same thing we did originally. That's fine. Okay? But I'm showing you this. Let's check this out here. If we were to simplify this here, this would be negative 3, negative 2, plus 5t, comma 3t. True? Then x would be negative 3 plus 5t, and y would be negative 2 plus 3t. Okay? All that does, gang, is guarantee that I'm starting at a point on the line and I'm moving in the direction of the line. Well, if I started at a point on a line and I move in the direction of the line the whole time, then I'm always on the line. No matter what t is, I'm always going to land on the same line. So that's an equation for every single point on the line. Okay? Another way to think about this too, if you want, if t goes up by 1, how much does x go up by? T goes up 1, x goes up by what? Look at these equations. If t goes up 1, how much is x going to grow by? No, that's not like common language for you guys? 2?
2 for x.
Every time t, yeah, we're multiplying. No, are you guys not answering because you don't want to, or you don't understand this?
Just subtract by 3.
If t, no, that minus 3 is like a starting point. Every time t goes up by 1, this expression is going to grow by 5. Because it's a multiple of 5. If t is 1, it's 5 minus 3. If t is 2, it's 10 minus 3. If t is 3, it's 15 minus 3. Every time x goes up 1, t goes up 1, x goes up 5. Every time t goes up 1, what's y do? 3. Well, what is that? If I'm starting here and x goes up 5 and y goes up 3, that's the slope. I'm just moving the slope each time. That makes sense?
Yep.
That's just, again, you could find slope-intercept form and just plug in a t for x. That's fine. Okay? But this is more using vectors and stuff to get those equations. It doesn't matter. They're both going to be the same thing for us because all we want to know is how to get the parametric in one way. Okay? Now, the real benefit of these things is motion. Okay? And we look at motion. First, we look at motion horizontally. All right, just in one dimension. And next year in calculus, like this is the most commonly tested topic in AP calculus, motion. Okay? We always talk about things moving in a line, like back and forth on a line or up and down in a line. Okay? So this is about me. I'm just so upset about summer that I won't be seeing you guys. That I have to pace back and forth and just fret over it. I don't know what you guys are going to get into all summer. You'll probably miss me too, I know. And I determine as I pace back and forth that an expression for where I am in relation to this breaker here between my chalkboard and my whiteboard is that right there. Okay? So if I plug in a time, that's just going to tell you where I am in relation to that. Okay? So imagine the front of my room is like a big number line. All right? And this silver bar here is 0. Okay? If I'm moving forward, then I'm moving to the right. Like in a number line, that's where the numbers are getting bigger, true? If I'm moving backwards, then I'm moving to the left. Simple enough? Okay. Now, we can graph this in function mode if we wanted to. Like I could go into, where do I got to go? Mode, function. And I could graph this equation. Oh, I just had it. Why did I do that? Come on, Glenn. Man, now I can't even move. Oh, the record is in the way. What is it? It's like negative 0.1 or 0.1 something?
Negative 0.1 times t cubed minus 20t squared plus 110t minus 85.
Minus what? 20t?
Yeah, squared
20x squared.
plus 110t minus 85.
Yeah, this thing is like so slow. Minus 85?
Mm-hmm.
Okay. So I'm going to graph this in function mode. Check this craziness out. There it goes. Now, keep in mind, I'm moving in a straight line up here, back and forth. Okay? My motion is not going to look like this curve. I'm not moving along a curve like a roller coaster. I'm moving back and forth, left and right, okay? What does this tell you? Like, how am I moving here? In terms of like this, again, this silver bar up here being 0, where am I starting? On this side of it, or the positive side or the negative side of it? For 0. 0 is in the middle here. Let me change this window to this. There you go. I'm starting on the positive side, right? I'm starting over here, like where the projector's shining. And which way am I going to head first? To the left. I'm going to head to the left because my position, which is this curve right here, my position is decreasing until I hit here. What's this point at the very bottom representing when I'm doing what? When I'm turning around. I'm moving backwards this whole time, and then forward, and then backwards again. Does that make sense? Why's what getting shorter?
Is the distance that you're traveling the curve?
Well, it just stops. I mean, the window keeps going here. Like we can go out to 15. Okay? I mean, so, and because it's a cubic, that graph's just going to go down forever. Obviously, I can't walk that way forever. I'm going to hit the wall eventually. All right? Y'all understand what I'm saying to you here, okay? But so the problem with this is, number one, is that's not actually my motion. If I wanted to graph what my motion was doing and actually see a picture of it, it wouldn't look like this, okay? I'm not moving left, right, and up and down like this graph is. I'm just moving left and right. So parametric gives us one way to solve that if I want to see what this graph looks like in terms of left and right motion, okay? So I can graph this parametrically, but now instead of putting, and I wish I could just copy paste this stupid thing, now instead of putting this in as y equals, okay, which is also weird because in my calculator I have y and x, but x on my calculator is really what variable? T, it's really time, and y is really x. It's a little confusing, okay? If we go to parametric, now when I graph this, which I have to type all in again, which is annoying, okay? Now I know I want my x to be negative 0.1 t cubed minus something, 20t squared, there it is, plus 110t minus 85. A better teacher would have had this already typed out maybe. Okay? Now, I can't just graph that by itself because you need a y. You need a y. Okay? But what's happening in terms of my motion to my height off the ground as I walk back and forth? Nothing. It's just not changing, right? So what could I set y as? We could set y as 0. There's nothing wrong with that. But if I graph it on the x-axis, it might be kind of hard to see, right? Because the x-axis is already there. So why don't we set y as like a number, like a little bit above it, like 3. Okay? Now when I graph this, we should see that exact motion we were talking about up here. I should move to the, so I got to do this backwards, to your left, and then to the right, and then back left again, right? But and keep in mind, remember I crossed through 0, and then I never got back to 0 again. I started heading towards it, but I never made it, right? So here's, this is not going to be a good window because now I'm graphing x, right? That was me walking back towards the middle of the room here. But now we can't see the rest of it because x doesn't go below 0. Before it was okay because x was time. Now t is time and x is where I am. So I gotta change my window again, which is a pain in the butt. So let's go from negative, there we go, negative 15 to 15. So here I am walking past that metal marker, and I stopped for some reason. I saw something I wanted. I'm going back to get it. Oh no, I'm pacing. That's right. I'm nervous. That's good. Never mind. Cool. I don't quite get to 0. It approaches 0 like we saw the graph do. And then I head backwards forever. And the other, well, time ran out there. But if time kept going, it would have gone left forever. Does that make sense? Now, the benefit of this is that you can see me moving left and right, back and forth. But the disadvantage is now it just looks like a straight line. You can't tell what I was doing at all. Okay? So something we could do, if I wanted to let this kind of rise a little bit as I was moving so I could see the whole thing, what could I do to my equations? What could I change? I'll give you a hint. It's y. What could I make y do? I can make a change. Yeah, I can make it a function so that it just goes up a little bit as time goes on. So what could I let it be? T plus 3? Well, really just t, right? T plus 3 will give us like a little bit off the x-axis, though. I like that. And I'm actually going to make it, since I don't want it to change too much, I'm going to make it like 0.5 t plus 2. Now remember, y has nothing to do with my motion. I just want to see what I'm doing left and right, and I don't want to overlap at all. Okay? So now when we do that, there I go. There's the left and right. Oh, and again, it stops, but I should be turning around there and going backwards if I change my t maximum to go to like, I don't know, 19 or something. Whoa, 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 whoa. No. That'll graph forever. There we go. And I go back, and then I go forward, and I go back again. Easy enough? So again, next year, questions like this might be this. Let's do this. Let's say I start here, and I'm telling you I'm starting at 3. Okay, positive 3. And I walk backwards to negative 5, and then forward again to 0. Y'all with me? One question is going to be, how far did I move? How far did I move?
8.
I didn't move 8. 3. I didn't. So there's a difference between how far am I from where I started. That's negative 3, actually. I'm negative 3 below where I started.
11.
I moved 13. Yes. I've moved 13. I went backwards 8, forwards 5. So distance traveled is 13, but displacement is negative 3. Displacement is how far you are from where you started. That make sense? Next year, you're going to answer questions like this without a calculator, though. It's going to be weird. Okay? But anyway, my question here was determine how far I traveled from 0 to 12. Well, so when I give you the numbers like this, that's easy, right? You know I went from 3 to negative 5 and back to 0. You can add that up. Okay? When I just give you this equation, what do we need to know? What do we need to know to find out how far I traveled? We know that I started out like here, and I moved. No, I'm trying to do this on your side. Here's 0, right? There's the room. I started here. I moved backwards, forwards, and then backwards again, I think, right? Okay, from 0 to 12. How can I find out how far I moved using this calculator? What do I need to know? I don't really need to know time. I need to know where I stopped and turned around. What position was this? Do we know that? This position here corresponds to what time? 0. How do I find my position at 0? Plug in 0. You can make a table, but if you plug in 0, look. All these t's are going to go away. 0, 0, 0, 0, 0, 0. You got negative 85 times negative 0.1. 8.5. Cool. I started at 8.5. Easy enough. I just plugged in 0 for t. To find out how far I went, I got to find this point right here where I turned around. Cool. If we go to my calculator, you can see it on the calculator. It's right there. In parametric, we have a couple options here under calculate. We have value, dy dx, dy dt, dx dt, which you don't know what they are yet. So we don't have, like, you know how in function mode we can find maxes and mins? We actually have to switch this to function mode to find the max and mins of this equation. Does that make sense? Which is kind of weird. Parametric mode shows you, why are you laughing?
When did I laugh?
Not you. You and you, there's eye contact. You're making fun of me. All right. That's fine. Okay. Yeah, that's fine. I have a complex. All right. So anyway, if you go back to function mode, even though it's turned sideways, how can I tell where I turned around? What do I need to know?
Like when you're going up and down.
Yeah, I need to know that point. What kind of point's that? I need to find the minimum right there. That's how far. Now, when I find that minimum right there, right here, it's a relative min, but do I need to know the x value on my graph or the y value, really? I want the y value on this graph because the y value represents my x value in real life, which is kind of weird. Okay, but the way we're going to find that is second calc, minimum is 3, and it looks like the minimum is around like 4 or something. I'm going to say look between 1 and 6 maybe, and I'm going to guess 4. Great. Wow. Oh, why's it got to be so ugly? All right. What's that, negative 9.9? Is that what it says?
I can't read.
8.9? Let's say 9.9. Let's just round it out to negative 10. Okay? Just to be easy. Negative 10. How far did I move on that interval?
18.5.
Okay. I moved 18.5. So far, I've moved 18.5. Easy enough? Now I got to find out where I moved to. So I'm going to go back to my calculator. Now I don't want to find the min. I want to find the max. Cool. So that's 4. Boom. It looks like it's around 10 maybe. I'm going to say look between 7 and 11. Great. I'm going to guess 10. Wow. And we get this number. Negative 1.2358. Okay? I'm going to say negative 1.24 for right there. So that's this value right here. Negative 1. I forgot already. 24? Cool. And that happened at time 9.4555, right? Now look, remember my time, I said how far did I move from 0 to 12? So now what do I need to know? Well, where am I at 12? I need to know what the value is at 12. Yes, ma'am. Cool. What are these passes for? Pictures? Okay. Yeah, you're good. You guys know how to find at 12? Isn't it a min or a max? I just need to know what point is at 12. You hit second, yeah. Trace, go to value, and type in 12. And I'm at negative 8.3, which we'll say is like right there. Can we find how far I moved?
Can you repeat your question?
Can we find out how far I have moved?
Yeah.
We need to do. We know 8.5 to negative 10 was negative, or yeah, 18.5, right? But then I need to add to that how far I moved to get to negative 1.24. How do I find distance? Yeah, negative 1.24 minus negative 10, right? That's going to be how far I moved to get back to there. That's 27.26. And I need to add to that how far I moved to get the other one. That's negative 1.24 minus, was it negative 8.3?
Yeah.
So all in all, I've moved 34.32. Did I put units on here? Units, yeah. Yeah. Does it say T is in, oh, X of T is measured in feet, it says. So it's, Because what matters is those points. Now, guys, this doesn't have to be in parametric equations. Okay, I just want to do like a motion question with you so you can kind of get left, right. It's always the question I get to answer. Yeah, there could be one of these on the test, yes. Okay, but it's 34.32. Okay? Meh. All right. So, this is really what we want to use parametric equations for here. The difference between motion in one direction versus motion in two directions. Okay? So, you should have answered questions like this way back in Algebra 2, okay, which was last year, wasn't that long ago, okay? But the reason why you see questions like this in Algebra 2 when you throw something up in the air is because once something's up in the air, the only thing acting on it is gravity, okay? And when the only thing acting on something is gravity, it has to move in a parabola, okay? So all that means is if you were to graph just the y function versus time, so let's think about this. If we graphed y versus time, it would look like this, where it starts out at 5. Okay? How do I know the initial height's 5 here? What do I do? Yeah, the plus 5. I plugged in 0. Yeah, the 5 is the intercept. Cool. Is the rock, when I throw it vertically up in the air, traveling in an arc like this? No. It's only moving horizontally in this graph because horizontal motion here represents time, and time is changing. Cool? If I wanted to graph just the motion of the rock, I would have to graph y versus x. Just like I did with my horizontal motion, I could let x be whatever I want. If I let x equal like 3, then the motion of this rock is going to it's going to start out at 5, it's going to go up, and then back down again. But you're not going to see, like once it's done, you're just going to see a straight line. You're not going to see what's happening. Cool? So it makes sense in a situation like this, and a situation in the last one, when it's only one-dimensional motion, it makes sense to graph that against time. Because then it's not laying on top of itself, and you can actually see like how the thing is moving. Just, I want you to keep in mind, please, that the graph against time is not what the rock is actually doing. The rock isn't moving horizontally. It's just going up and coming back down. Okay? Which is different than, now this is the next question down the bottom here. I'm kind of skipping ahead a little bit. Which is different than a graph like this, y versus x. That's what the motion would look like right here if I was to throw a rock at an angle up into the air. The problem with that graph now is, although that is what the rock is doing, there's nowhere to incorporate the time when it's hitting there. And that's the purpose of parametric equations. We look at x of t separately and y of t separately, and we can think about what's happening to the thing vertically and horizontally. Everybody with me on this? Okay, so the kinds of questions we really want to answer are projectile motion questions like this, where y and x are both changing with respect to some other variable, namely time. Okay, so this question here specifically says, how high does the rock go? Using my calculator, I'm not going to do it. But I hope you all can graph this in function mode and find that maximum value. Cool? Anybody remember how, without a calculator, to find the maximum of a parabola? There was a formula for it. It happens when the independent variable is. It's part of the quadratic formula. When x is negative b over 2a, that's where the vertex has to be always on a parabola. Is that okay? It's proven. Cool? So you could plug in, so that would be in this case, negative 76 over negative 32, which is 2 point something, right? But that's not the max height, that's the time it hits it. How do I find the max height? Plug it back into the y thing, okay? We use calculator, I hope you all can plug in, you'll get an answer. Sound good? Okay, so everyone understands the difference between graphing y versus time, x versus time, and y versus x. Yeah, you all look super thrilled about this. Excellent. Okay. Later on, just to skip ahead here a little bit. Horizontal motion, I know I'm skipping this question. We'll do this question tomorrow. Horizontal motion depends on only one thing. Okay? The speed at which your thing is moving horizontally has only to do with how fast you throw it horizontally. Okay? Like once it leaves your hand, the horizontal motion is consistently the same thing. There's nothing else acting on it. Vertical motion has to do with 3 different things. What affects vertical motion? Gravity is one of them. I'm going to put that over here. What else affects horizontal motion? If I want to throw a rock but go higher than the last time I threw it, I can't change gravity. What do I have to change? Force. I'm going to call that the initial velocity, v sub 0. Okay? Well, angle is not, you're very correct. All right? But I'm going to call it v sub 0 in the y direction for right now. Okay? But just vertical, the initial velocity, we'll say. And then the last thing that affects it is if Taeyong and I each throw the same exact weight with the same exact force, but he's standing on top of a building, his is going to go higher. So initial height also changes motion. Okay? I'm going to call that S sub 0. Let's call it H sub 0 just so we got something. Okay? Those are the 3 things that change motion. Yeah. Yep. Okay? Now, the only one of those that you cannot control unless you want to travel to the moon or something is gravity. Okay? So gravity, just so you know this, is a constant on Earth. Well, it actually fluctuates depending on your altitude, but we'll say it's a constant for us. Anybody know the units on gravity, like what it is?
9.8 meters.
Negative 9.8. Look at all these smart physics kids. Negative 9.8 meters per second squared. Or if you want to do feet, it's negative 32 feet per second squared. Okie dokie. And that right there like dictates how anything on Earth that's not being propelled into the air like a plane or something has to travel once it hits the air. But that's it. Excellent work today.